Hi, everybody. My name is Ron. It's time to dig into the subject of slow flight and stalls and energy management. This is area of operation 10 in the Flight Instructor Airman Certification Standards, and all of this is relevant to anyone who decides they want to fly an airplane. So whether you're working on your pre-solo or your flight instructor certificate, this could be helpful to you. So let's get started. If you look at the top drawing, you'll note that the angle of attack is depicted here as the relative wind and the angle at which it encounters the wing in flight relative to the chord line of the wing. The chord line, of course, is the line drawn directly from the rearmost part of the airfoil or the wing and the very front part of the wing. So it's depicted here with a red line that shows the angle and the alpha or angle symbol, and that's typically measured in degrees. The number of degrees of that angle are not depicted here, but that's not really important right now. Each wing behaves differently depending on the angle of attack. And we'll get to know our own airplane better, but it's important to know the general concepts because we're not just going to fly one airplane. This next drawing depicts the coefficient of lift against the angle of attack. Coefficient of lift is the vertical axis in this drawing, and the angle of attack is the horizontal going off to the right. Now, as you can see, the greater the angle, as you get to 5 to 10 to 12 degrees, the coefficient of lift goes up. Now, until you get to a certain point, the point where that's maximized is called the critical angle of attack. So here you can see that somewhere around 13 degrees, the wing that this drawing is based on reaches the critical angle of attack. When the critical angle of attack is reached, you have what we call an aerodynamic stall. That is a point at which the smooth airflow flowing over the top of the wing, as you can see in our leftmost wind tunnel depiction, the air is flowing smoothly around the entire airfoil. In the right-hand picture, the angle gets too great and the air flowing over the top of the wing starts to swirl and delaminate, come away from the surface of the wing. This spoils the lift and causes a great deal of drag. So it goes from being beneficial to almost just like that, depending on the wing design, absolutely detrimental to lift. As we look at this drawing, we'll start at the top. The wing depicted in this drawing is a wing that is increasing its angle of attack. As it starts to go up very noticeably, you start to see separation at the trailing edge of the wing. And at that point, you end up with what they call a turbulent wake. That causes quite a bit of drag and spoils some of the lift. As the angle of attack gets higher, as in the center depiction, the turbulent separation point, the point at which the air no longer adheres to the top of the wing, starts creeping up towards the front. And that's a sign that the wing is about to fully stall. Now, taking a look at the lower drawing, item C, it calls out stalled flow conditions, where the separation point is right about that transition point depicted in the upper drawings. This wing is fully stalled at this point. It's generating virtually no lift and quite a bit of drag. That's a stall. This next drawing depicts induced drag, parasite drag, and the blue line, total drag. I get this from the Bold Method website, which is a fantastic site. I recommend you visit, run by a qualified flight instructor, so it's good information. There's quite a bit more there. That said, I'm going to define induced drag, parasite drag, total drag, and then go into a little bit more detail on what this means to you as a pilot. Parasite drag is a combination of form drag. That's the drag caused when air decides it's going to go around an airframe, the wheels, things like that. It can be experienced if you stick your hand out the window of a car on the freeway. You'll feel the wind pulling your hand backwards. There's also skin friction drag in parasite drag as well, but they're both of those are combined for parasite drag. Induced drag's interesting. Induced drag is the drag that is created by the creation of lift. Now, these curves, as you can see, move opposite each other when airspeed's increased. Airspeed is depicted left to right. On the left is low airspeed, 0, and on the right is 120, 130 knots. Now, the vertical component here in this particular chart is drag. It says pounds. It could be tons depending on your airplane, but you get the picture. The drag increases however you measure it, or whatever unit you measure it in, as you go vertically. Now, as you increase in speed, parasite drag ramps up. You can see that. Now, if you experience the sticking your hand out the car window, safely please, you'll note that as you accelerate, it pulls back even harder and harder on your hand. Now, induced drag, it's plotted in opposite of that. At low speed, near stall speed, that is the minimum airspeed at which we can develop lift, that's why it stops there. At low speed, it's very high. As you accelerate, the angle of attack decreases, and you develop less induced drag as you go faster. Now, the blue line is total drag. If you ever took calculus in school or learned to plot things on a graph, total drag is the induced drag at a given airspeed plus the parasite drag at a given airspeed. And there's a point at the bottom in the middle where that is at a minimum. This particular chart introduces a few new concepts. The first one, we'll start at the top, is the power available line. That shows us, oh, we're not going to draw for me. That shows us the amount of power we have available at a given airspeed. It's not straight for various reasons we won't go into now, but note that certain aircraft are able to develop more power at higher speeds, and some airplanes are better down low, and the power drops off later. So the power available curve is plotted here. We've got power vertically and speed horizontally here. The next thing I want you to notice is the excess power available. Now, this depends on the particular point in the chart that you are, the particular airspeed you're flying at. And there is a point here where that is at its maximum point. This curve, the power required curve, looks a lot like the total drag curve, and it is because it is a function of total drag. Okay, so one is based on the other. So the more drag you have, the more power is required. Now, this is the point where we have the minimum of drag. Okay, that's where the airplane is the most efficient. Here, we call it the minimum power speed or minimum power required speed. Okay, this is really important. If you are this far along in your ground school, for example, you'll note that that is typically really close to your best glide as well, and your maximum endurance speed. Maximum endurance because you need the least amount of energy for level flight, and best glide speed, roughly, because you need to trade the least amount of energy to maintain your airspeed at that speed. So then we also denote that this red line represents the stall speed. Most of us have heard the term being behind the power curve. Now, that gets applied to a lot of things these days, but that term came from aviation. Now, if we look at our diagram here, we have a line at our minimum power required speed, the point of minimum drag, and it's labeled backside and front side. Now, if we were to look at our previous drawing from the bold method, speed was depicted across the bottom, just like this one, but it had drag depicted up the right-hand side of the drawing. This is, in essence, the same drawing, but it wants to communicate that you've got speed at the bottom that increases from left to right, and power required for maintaining level flight that goes vertically. Now, you could leave drag on the right-hand side of it because this is a drawing that shows speed versus drag as well, okay? But we're going to look at speed versus power required. So if we were to take a look right here at the minimum power required airspeed and say, gosh, we're cruising along, we're being really efficient, we're pretty slow at that point. We're talking 65, 68 knots maybe, clean in a lot of general aviation airplanes. We're cruising along and we decide we want to go faster. We're going to have to add some power, right? As we want to go faster, there's more power required. This operates just like any other motor vehicle in essence. But we're talking about flying an airplane where we actually have to generate the power to keep ourselves in the air. And power creates speed, which creates lift. The slower we are, the less lift we create and the more drag we create trying to compensate, right? So this is what's called the region of reverse command, because unlike going faster from this point, you need more power. To go slower from this point, you need more power. And boy, does that curve get steep. So if this were 68 knots, the best glide of a general aviation airplane, and we wanted to get down to 48 knots, which is just above the stall speed of some general aviation airplanes in the clean configuration, we are going to have to initially pull out a little power to slow down and then increase our pitch. But as we slow down, we're then going to have to start feeding in more and more power as we get slower. So it's entirely counterintuitive and backwards. It's opposite day from what happens when we're on the right side of the minimum power airspeed. So the region of reverse command. Now this is a truly, truly interesting diagram. Looks really familiar once again, but it calls attention to a new concept. Now, they haven't bothered plotting out the minimum power required speed, but we can see it down here where my cursor is. Imagine that you're up here at the speed at point A. This looks like maybe 75 knots. We'll call it that, hypothetically. And we decide we want to start flying slower. We want to get into slow flight. So initially, we start raising the nose, perhaps right off the bat to kick it off, pull out a little tiny bit of power, but immediately we're going to have to start adding some power as the airplane slows down and our pitch increases, we get into slow flight. Now, here's the good old power available line, okay? It intersects on the right side with the power required, and this, whatever that number would be, would represent the maximum speed that we could fly that airplane, right? That's when the drag meets the power available and we hit equilibrium at full throttle, for example. As you begin to slow down from point 1 to point 2, from A on the power availability curve to B on the power availability curve, and it meets the power required curve, you can actually fly at that speed. That's the minimum sustainable airspeed, the minimum level flight speed that you can fly. Now, obviously, If you look at the drag curve here, the power required curve, it's depicted both ways here. It actually goes slower than the power available. So imagine that you're flying along here at the B point, you're at full throttle, you're at the minimum level flight speed. If anything occurs at that point, you hit a little wind shear that changes your angle of attack. You let slip a little extra back elevator. Something like that occurs. You hit some turbulence. You're going to go below that speed, and once you do, you can see how steep this is. You only have to slow down a couple of knots before you get to your stall speed, which is depicted at C here in 3. So at this point, this is so steep in almost all airplanes that this is point B is a really precarious position. Okay, you're going to want some, unless you intend to stall the airplane for training purposes, you want to stay at least a handful of knots above that. Okay, so the important takeaway here is this is called the region of irreversible rate of energy depletion. If you maintain flight there, the airplane will stall. If you are somewhere between B and C and you recognize it soon enough, what can you do? At that point, you've got no choice but to push forward on the yoke, reduce the angle of attack. You're going to lose some altitude and get yourself back to the right side of this yellow number 2 airspeed. So you can always control things with pitch, but at this point, between B and C, you can't control things with throttle. That's the big takeaway. The region of irreversible rate of energy depletion. It's just going to, because of that high drag, your energy is going to go away and the airplane is going to stall unless you act immediately. Now, one takeaway that I want you to walk away with is that this is a power required chart, okay? And if we're sustaining level flight and keeping our power set for this particular point in the chart, for example, where my cursor is, solid line below the middle, for example, let's say the minimum level flight speed is 47 knots in this particular general aviation airplane in this clean configuration. Let's say this line represents 50 knots. And on the front side of the power curve, that same power setting will net us perhaps 100 knots. You go down here, this could be 58 knots, and this could be 68, 70 knots. 2 different speeds, same power setting on opposite sides of the power curve. I think that's a really powerful takeaway. And when we get into Area of Operation 10 Bravo, we're going to talk about how you can fly yourself from one side to the other of that same setting without touching your power. Stay tuned for that. Well, that concludes our section on the aerodynamics of slow flight, stalls, and everything that we covered. Keep these concepts in mind at all times. Remember about the region of reverse command and recognize what happens and what you have to do. You've got to add power to fly in that region. The slower you go, the more power you have to add. That drag curve, the power required curve, is really, really steep. So the closer you get to the intersection of the power required curve and the power available curve, the closer you are to an imminent stall. So keep those in mind as we go through our next lessons on the various types of stalls, slow flight, maneuvering during slow flight, and maneuvering in various configurations.